Okay, shall I go? Okay, hello. So to give you a bit of context before I start, my name's Clare Sudbery. This is a bit odd actually. I'm looking for an audience to look at. So I'm going to look at Alina. There you go. You're my audience. But that means the camera can't see me. So I'm going to have to look at you. There you go. My name's Clare Sudbery. I'm a software engineer. I've been a software engineer for the last 17 years or so. Actually, not the last 17 years because there was a gap in the middle, but that's just me being pedantic. I'm a senior developer with ThoughtWorks. I'm currently working as a tech lead at Stockport Council. I have half a maths degree. So I studied maths and philosophy at university a very long time ago, more than 20 years ago. Which gives you some context for what I'm going to be talking about today. And I'm mainly going to be talking about maths in the context of graphics. None of this is professional. I've never done this for my job. It's all very, very amateur. But what I realized when I thought about all of the various different software projects I've worked on in my spare time, that they have all involved maths and graphics. Now, given that they've all involved graphics, that's not a massive surprise. And it's not that much of a surprise that there's always been graphics, because I quite like things to look nice. I like visual things, and graphics tends to be very mathematical. But when I was looking at all the various examples I'm going to show you today and thinking about the various things I've worked on, I did realize that they have something in common, which is that there's always a bit of a guilty secret that I have a tendency to do things the long-winded way. And I've always thought, in pretty much every one of these projects, while I've been working on them, I've thought there is probably a better way to do this. And I've never actually gone to look up that better way. And that's the guilty secret, because as a developer, that's not really very good practice. But what I realize is the reason that I do tend to do things the hard way is because I really enjoy doing it that way. And these are all projects that I've done for fun. I like maths. So I quite like it when I have to get my hands dirty and think about the numbers and think about the maths. The maths that I'll be talking about today, none of it is particularly sophisticated, because although I do have half a maths degree, it was 20 years ago. And actually, I don't remember most of the difficult stuff. I also should mention, when I said that my 17 years as a software engineer weren't continuous, that's because in the middle of that, there was a gap where I did a couple of other things, one of which was to retrain as a high school maths teacher. So my GCSE maths is quite fresh. That was only 5 years ago. And to be honest, most of the maths in here, I don't think it really goes beyond GCSE level. So it's not actually that difficult. But I suspect that you could probably do a lot of the things that I've done without needing to know much maths at all, because there are probably tools out there, there are probably libraries that do these things for you. But as I said, I have tended to go the long-winded way just because it's more fun for me. So I'm going to start talking about CSS animation. So that thing that you see on the screen at the moment is a CSS animation that I made. And it all started at a previous job when I went to a talk on CSS animation. Oh, hang on a minute. I've just remembered I do have some slides, and I feel like I should show you this slide, not that one, because I like it. So anyway, yes, you should all come to the maths side. But anyway, so I went to this talk. It was a brown bag session delivered by a colleague, and he was just introducing the basic concept of CSS animation. And so he was just showing us some very simple animations. And one of the things that he showed us was this idea of having the sun apparently rising and setting in the sky. And after I'd been to that, I thought, well, can I make that sun move in a curve rather than in straight lines? Because obviously that's not actually what the sun does. So I had a go. This was my first attempt. Now, this was me going the really, really, really long-winded route. What I did in order to get this moving more or less in a curve, you'll see it's actually a little bit jerky. The colours were just me playing with colours. What I actually did in order to get that was I had a spreadsheet where I calculated all the different points so I plotted some points basically, and I did some maths to work out what the X and Y coordinates should be when X goes from 10 down to 0 and back up to 10, and actually then to minus 10. So it's starting over on the right hand side and moving over to the left. And oh no, no, sorry. So yeah, it does. Anyway, I'm not going to even attempt to go through this maths in too much details, but it was quite a lot of work went into it, and it was a completely insane way of doing it. And I knew that at the time, but I kind of got the bit between my teeth and carried on anyway. So that was my first attempt. Then I used a timing function. So this was my second attempt. This is using a timing function. Now, as you can see, it's kind of doing a bit of an oval shape at the moment. If I resize the screen so that I have a square, then it looks a bit more like a circle, but it's pretty rubbish. So if we that go bigger again. If we look at what's actually happening behind that, so if I show you the CSS, that was this one, not that one, this one. So this is actually using a Bezier timing function. So it's this animation timing function here, and it's using the cubic Bezier function. So to show you, give you a bit of an idea of how I worked that stuff out, you'll see it does actually do it. It does it 4 times. So what I hadn't worked out at that point was how to make it repeat. Make this. Zoom in. Oh, right. Yes, sorry. You know what? I'm not used to using Sublime on a Mac. Anybody know how I zoom in? Command plus. Like that. There you go. Is that better? Is that enough? More? Yeah, cool. So you've got these Bezier functions. So to go back to my slides, that is this stuff. So what I wanted was an arc that would allow me to move fast and then slow, and another one that would go slow and then fast. And if you look, what I've done is I've divided the circle into quadrants, and in the top left quadrant, I want X to increase slowly and then speed up. And I want Y to start fast and then slow down, because if you look at what's actually happening to the X coordinate as it goes from left to right, it increases slowly and then it increases quickly, and the Y is opposite. And in each quadrant, it's the opposite way around. So I picked the Bezier curves that would achieve that for me. And the way the Bezier curve is that you give it a starting point and you give it a starting kind of tangent, and you give it an end point and an end tangent. So I actually started vertical and ended up horizontal. And I had 4 of these Bezier curves. I also had, so this one was about going fast, slow. This was about going up and then forward, which was another way of thinking about it. In this case, I used the numbers 0.35 and 0.65, which is why that looks a bit less circular. I'm not going to go into the maths, partly because it's complicated and partly because I've half forgotten it. But in fact, I think what I get from this is not what I thought I was going to get. I thought that I would get a quarter of a circle by doing this, but that in fact is not what I get. My dad, who's a math professor, did explain to me why I don't, but I've forgotten. But if you can see, that's not really, even when I resize the screen, it's not really quite a circle. And also the timing of it is really weird. The whole fast slow thing gets kind of doubled. It doesn't do it in the proportions that I thought it would. So that wasn't a brilliant solution either. The next solution I had, wait a minute, have I done? Yeah. So the next solution is, that's the spreadsheet one, that's the timing function. The next solution is the best one. I don't know if you can see that. It is a yellow dot, but because it's yellow, it's a little bit hard to see. And it's just in the bottom of the screen, and it's just doing half a circle. And it's also moving smoothly. So the timing is correct and the path is correct. And the way that I achieved that is brilliant. It's and I can't take credit for it, because this was me finally giving up and actually looking it up and finding an idea from somebody else. I googled it basically, but this is lovely. Look at this. So this was what it looked like when I was doing the timing function. There's quite a lot in there, and there's some more stuff down here. This is using rotation, and all it does is it rotates and it moves. So if it were to rotate and not move, so this translate is saying move 300 pixels to the right. And the rotate, if I didn't have that translate, it would just mean that if it wasn't a circle, you would be able to see it rotating on the spot. Because it's a circle, you actually wouldn't even be able to see that. But if it was a square or something, you'd be able to see that it was rotating. The translate is being used at the same time. So when you're doing animation in CSS, you always have a from and a to, and you're saying transform from this to this. And it's transforming from a 0-degree rotation to a 180-degree rotation, but it is also translating to the left or the right. But it doesn't look like it is, because it looks like it's going from the same translation to the same translation. But because it is also rotating, the two combine to mean that the whole thing rotates around a central point. And again, I confess, there was a point at which I totally understood how that worked. And now I'm beginning to think I'm going to have to go back to first principles and work that out again, because every time I look at it, I'm like, that is super clever. And it's not obvious that it would work, but it does. So the next thing that I wanted to show you was this. But before I show you that, I'm going to explain why that is there. So this is a piece of software that I wrote actually quite a long time ago. And I'm going to start a video off of the software running, and then I'm going to explain what it's doing. So this is a card game, which I call Top Game. It's not actually called Top Game. It's official title. It has lots of titles. It can be called Beg Your Neighbour, Beat Your Neighbour Out of Doors, Strip Jack Naked. It has lots of names. But the way that the game works is that the pack of cards are dealt out to the players so that it is evenly shared amongst the players at the start of the game. The players are not allowed to change the order of their cards. The players don't even have to look at their cards. The game is more fun if you don't look at your cards. The players take it in turns to play cards, and you keep playing until one of the players plays either a face card or an ace. At that point, the other player has to pay the player who's played the face card. If there's more than two of you, then you're just going around in a circle. But it's quite, I think it's more fun when you play when there's only two of you. So the other player has to pay you. So it's 1 for a jack, 2 for a queen, 3 for a king, and 4 for an ace. If while they are paying you, so they pay you by playing cards, they have to do them one at a time, because if while they are paying you, they play a face card or an ace, you have to pay them. And what's really interesting about this game is it's really good fun, even though there is no skill involved whatsoever. The cards are dealt to you, you play the game. You're not allowed to change the order of the cards. That would be cheating. It's entirely deterministic. At the beginning of the game, the winner is already determined. But you see this number on the bottom left of your screen. That is how many possible games there are. So there are an awful lot of possible games that can be played. So let me go back to my slides again. The number of games is that. If you played one game per millisecond, it would take 20,780,000 billion years to play them all, i.e. nearly 21 billion years. No, that's, 21 billion years anyway. The universe is apparently 4.5 billion years old, so it would, take a really long time, and that's per millisecond. So there's actually a lot of complexity in there. The reason I originally wrote that code was because I wanted to know whether it was possible to have an infinite game. And I haven't actually been able to answer that question. But what's interesting, this game that you're watching now, this is still the same game. Games can, like, this video is about 4 minutes long, and this is speeded up. So games, what's really interesting, in fact, you're watching it now, there's a reversal of fortune going on. What you're looking at is the two players' hands are at the top of the screen, and the cards that are in play are at the bottom of the screen. And you'll see that the cards that are in the player's hands will quite often go down to only 1 or 2 cards, and you will think surely they're about to lose. I can see that the player on the right is actually doing really well at the moment because they've got 2 jacks. Jacks are the most powerful cards because your opponent only gets 1 chance to beat you if you play a jack, because they only have to pay 1 card. So unless that card is also a face card, you have won that hand and you get to pick up all the cards. And one of the things that I notice when you play is that it feels like there's a rhythm. It feels as though face cards are attracted to each other. They tend to cluster together. And I wanted some way of visualizing that. And this is what I came up with. So the idea of being able to visualize the cards that are in each player's hand and to see where the face cards are. So the non-face cards we tend to call spuds. Me and my partner, who play this game a lot when we're drunk, and spuds are useless, so they're just white. But one of the things that you notice when you're playing is you see, now that player on the right is surely about to lose. Yes, finally they did, because they only had a dark blue card, which is dark blue card is a queen. So actually, queen's not bad, but they only had 1 queen, and they lost the game. So in order to write that, there was quite a lot of maths. So if you look at this diagram here, I don't know how well you can see that. Oh, why can't you see that at all? That's strange. I think this display's frozen. There you go. So that is a diagram that represents one of those petals, as I call them. And it's looking at all the different angles that I have to calculate when I'm making a petal. And the way that I do it is that I allow the petals to grow and shrink according to how many cards somebody has in their hand. So the angle at the center grows and shrinks. And then when the angle at the center changes, that means that and also the lengths of the arms of the petals change. It also means that the arc needs to be recalculated because the radius of the arc will change. So there's quite a lot of maths going on all the time to calculate all of those things. So just to remind you, so the 2 bits of maths I mainly use when I'm making the petals are something called SOHCAHTOA, which is sine, cosine, and tan, and Pythagoras. So to remind you how Pythagoras works, if you have a right-angled triangle, then if you take the length of the vertical and horizontal sides and square them and add them together, you will get the length of the hypotenuse, which is the diagonal side, squared. In the context of a circle, this is really useful. So this is how I used it within the context of that game, because I have those petals that all have an arc at the end. In this case, the hypotenuse is actually the radius of the circle. Because I'm plotting points on the screen, I need to know the x and y coordinates. So that's why I'm using Pythagoras there. SOHCAHTOA is also useful when you need to calculate the lengths of the other sides. So if you know the sine of angle A, you will also know that it is the opposite side, which here is y, over, sine is opposite over hypotenuse. So sine of A would be the y coordinate over the radius of the circle. Or if I know the angle and I want to know the coordinates, then I can use cos is, tan is opposite over adjacent. So to have a quick look at what that looks like in the code. And here, again, I have a confession, which is that, wait a minute, I just need to find the code, which I've lost. Is that it? There it is. The confession is that this code, this particular piece of software, so is this thing, was developed for Genius Day at a previous employer. Genius Day was where you had 1 day to work on some code and then present it the following day to your colleagues. And I actually, because I knew it was coming, I had in fact been developing this for weeks in advance, but I'd only been doing it in my spare time. And also at that point, I'd been out of the industry for 4 years. I'd only just come back in, was learning a whole load of new stuff, could only barely remember how to write code at all. And I was writing it at great speed. So the code at that point was awful. It was really, really, really bad. So I had methods that were like hundreds of lines long with millions and millions of variables that were impossible to keep track of. I have refactored it a bit, but it's certainly better than it was. But it still has weaknesses. But here's an example, shall I make this a bit bigger, of the kind of thing where I'm doing some maths. to calculate things like the lengths of lines. In this case, I'm trying to move along a particular line so that I can work out the segments for the cards. So here's my maths here: get adjacent side, get opposite side, given the angle. I've got a tan here. This kind of thing. This is where it's calculating things like the length of an arm segment, the length of the central spoke, which is the bit in the middle of the petal. Where's the bit with a giant comment? There, here's a bit with a giant comment. This is explaining how arc paths are drawn, because at first it took me ages to get my head around it. Actually, that is a lot of text. This is a much better description. So when I'd finally worked out how it worked, I drew this diagram, which when you're drawing an arc, using the library that I was using, you need to know what your start angle is, which is measured from the left. You need to know what your sweep angle is, which is this one here, and the arc will be this line here. It's done on an ellipsis. So if you're enclosing, you also need to define your enclosing rectangle. If your enclosing rectangle is a square, then you'll get a circle. But it doesn't have to be a square. And of course, a square is in fact a rectangle. It's a special case of a rectangle. So I think probably that is enough maths for you all. The reason this is here is because I was investigating how I could implement the same code we were just looking at, but do the front end in a browser, because at the moment that is actually a Windows desktop app. So this was looking at whether I could get the same effect in a browser. This is using HTML5 animation. There's the code there. I won't bother trying to explain that now, but there's a similar thing going on when you're drawing arcs. You can make things overlap. So the way I got the petals was that I drew rectangles and triangles on the screen, and I drew an arc. And then where the two intersected, that gave me the segments, so that I could have different segments for different cards. So you see there's different segments. And just for lols, I will also show you some of the other things that I've done with CSS animation. That is just two people moving backwards and forwards. That's two people moving backwards and forwards, but playing with shapes and colors and the transitions. That is Marge and Lisa Simpson being transformed one into the other. So the reason obviously it needs a bit of work because there's gaps, but the reason I could do that is because I didn't draw them originally. There is a site, you can look it up, Simpsons CSS. Somebody has drawn the Simpsons entirely using CSS. And the way that they've drawn Lisa is by drawing a load of yellow triangles. And actually, I think there's some rectangles in there as well. And then they've made them all overlap. The way that they've drawn Marge is by drawing a load of circles for the edges of her hair and then a big oval in the middle. So what I did was transform the circles into the triangles and back again. Again, just for fun. This is the one to hypnotize you all at the end of the talk, and I think that's everything. So, any questions? Have you tried E3? I haven't. No. So the question. Yes, I was just about to repeat it. So, is it E3JS? D3JS. You see, I don't even know what you're saying. So the answer is definitely no. And actually, I would like to. So I haven't done anything with SVG really either, and I'd like to try that, particularly in terms of, because this time I am going to do a bit of due diligence. And if I put a web front end onto the game playing software, then I would actually like to choose the best technology before steaming ahead. Mm-hmm. Yeah. Yes, I was about to repeat everything that he said, but why don't we just go on, say that again.
I was just saying it would be easier. You get the abstractions over like units that you get on HTML5 and Canvas to build what you're working. You can focus on the visualization bit only.
Brilliant. I shall add that to my list of things to investigate. Any other questions? I'm going to take that one off because it does actually hurt your eyes after a while. Are there any? I can't actually see my view screen at the moment, so I need to bring that in. But now everybody's going to see Fuse. No, I am screen sharing, aren't I? So I can't get it to come in now. Has anybody got is right? So there's no questions coming in over the line. So any more questions? Cool. Okay. Thank you for listening. There it is.